Okay, now I didn't do examples of the 102 and 103 problem because they're so similar to the other. You just have to construct a different function, but you do all the same things. The function looks different, but you know that. Okay. Now we go to the next problem, which is the inverse function. So we're not going to set up this. So we're given coordinates of 4 points. We put those in the table, and we plot the points. Negative 1.6, negative 1.6 is here. And of course, we do all the construction lines and everything. And this is a basic toolkit function. So it's in a 4x4 rectangle with the red dot at the origin. Okay, that's true for any basic toolkit function. Now the toolkit shape doesn't have coordinates on it until we tell you where the red dot is and what the size of the rectangle is. The difference between the toolkit function and the toolkit shape. We're going to take note of that. Anyhow, we plot these points. Now they're plotted in point here, 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 and here. Then we draw a nice smooth curve through those points, and we get a curve that looks like a white curve. Then, well, what's an inverse function? We swap x and y. So we come down to the tables here. We swap the x and y values. The y column here becomes the x column, and the x column becomes the y column. You can see that clearly. And we plot points. We see that the inverse function, in this case, kind of wraps around the original function because of the shape of the original function. Okay, well, that's legitimate. That could happen. Now, it turned out that this didn't work out very well for an example, and I'm going to have to change the algorithm in this function a little bit. What you were asked to do, and I'll have to address this in another video probably tomorrow because it won't get done today. It's getting late. Definitely got to eat. Okay, so you're asked to evaluate f inverse of 1.6. Okay, well, x equals 1.6 is this line. It intersects our graph of our actual function. Actually, I think maybe I did that wrong too. It intersects our function more like here than here. No, I'm sorry, that was f inverse. So, okay, we intersect, this line intersects our f inverse function here. It gives us a y value. Okay, now I didn't actually put the y value in the graph. I think you get it cluttered, but that's real close to 2, so I called that 1.9. So I said f inverse of 1.6 is 1.9. So it kind of made a one line table. X is 1.6, f inverse of x is 1.9. Got the 1.9 in blue because it came from the blue graph, which is graph of the inverse function. And I've got that table for the inverse function circled in blue too, so you see. Then I let s equal that, and we find f of s. That's what you're asked to do, which would be f of 1.9. Well, this doesn't work out too well because we let x equal 1.9. We come up here until we intersect the white graph. It doesn't even intersect the white graph. So things kind of fall apart with this example. But that's what you're asked to do. And then you're asked to find r, which is f of 0.8. Now that works a little better. Here's x equals 0.8. We're trying to find f of 0.8. F is the white function. So 0.8 goes up here and intersects white graph at this yellow x, which corresponds to about y equals 0.7. So we get f of 0.8 is 0.7. Then we want to do f inverse of r. Well, f inverse of r is your 0.7. F inverse of 0.7, and that's not written very well, is well, so f inverse, that one's too long, and you almost not see the negative yet. And I don't seem to have any bright chalk handy yet. Okay, it says f inverse of 0.7. Get f inverse of 0.7, you make the line for x equals 0.7. I didn't label it, but right here it is. It intersects this graph up here, and we project this point over, and we find that it looks like y is about 0.8. So that works. Now, what this tells you then is that we're looking at F inverse of f of x. This is F inverse of R, and R is F of 0.8. So graph F of 0.8 is 0.7. And F inverse of 0.7, according to this graph, is 0.8. Now, what I was trying to do here was S was F inverse of 1.6, so F of S would be S F of F inverse of X. So we'd be finding F of F inverse of 1.6 equals what? Well, again, the graph didn't really allow us to do that. So I'm going to change these functions so the graphs are a little less tricky. And when I get these tests into the testing center either tomorrow or hopefully Saturday, depending on just how much rain we get from this hurricane, because we've had, at my house, we've had 7 inches of rain in the last 5 days and 4 of them last night. If we get 4 more inches of rain from the hurricane, a lot of people in the county aren't going to be able to go anywhere for a while. So we would be closed down. Now, I think hopefully by Saturday, most of the flooding will be over in this area because of the steepness of the ground and stuff. Things drain pretty quickly, but I think we're going to get pretty wet potentially. 7 inches of rain in 5 days right before a hurricane comes. So it's not going to be good for some people. I'm sorry about that. We needed the rain, but we didn't need nearly that much. We need as much as we've got, and we're likely to get a lot more. Okay, well, anyhow, that's the status on this function. Now, we do have another problem related to inverse functions, which is pretty easy. And I think everybody is pretty good with that. But let's look. The 105 problem on inverse functions. And it's simply, as soon as you see inverse function, you write down inverse function, swap x and y, or just swap x and y. Just remind yourself that that's what happens with inverse function. That's what happened with the graph that we just looked at. We made a table of the 4 points, and then we made a table where we swapped the x and y columns and graph that one. That's very easy to do. The estimates in the graph should be easier to do than they were on that one, but I just screwed up when I designed the problem. Okay, didn't really discover it until I tried to work it. Okay, anyway, you give an f of x equals negative 4x plus 4, we want the formula for that inverse of x. I'll tell you in advance, if you want to see me make a few really bonehead mistakes, I go back to the full video on this, and you'll see some if you want to get a good chunk about it. But anyhow, f inverse of x, f of x is negative 4x minus 4. What's the formula for f inverse? Well, f of x equals negative 4x minus 4 means kind of y equals f of x equals negative 4x minus 4. So it means y equals negative 4x minus 4. And now we swap x and y. Right, the word swap, as I was explaining it as we went. We get this, and I think everybody understands that. Everybody's doing pretty well with this. So we swap this and solve for y. I'll go through the steps of solving for y. They're simple. We get y equals negative x plus 4 over 4. So that f inverse of x is y equals f inverse of x is now negative of x plus 4 over 4. The negative goes in front of the whole fraction. Now we want to verify this. How do you verify? And this is a little more challenging part. You got to remember how to verify inverse functions. And it just comes down to f of f inverse of x equals x and f inverse of f of x equals x. Now we do that, it's very simple. F of f inverse of x is negative 4 f inverse of x minus 4, just replacing x with f inverse of x here. and f inverse of x was found to be negative of x plus 4/4. So we replace f of x with that. We get x plus 4 minus 4, and that's equal to x plus 4 minus 4 without the parentheses. 4 minus 4 is 0. We get x. So we verify f of f inverse of x equals x. You also have to verify f inverse of f of x equals x. And that's pretty much as easy as this one for this function at least. Sometimes they're tougher, but I'm not giving you any tough ones on this test. Save those for later. Okay, f inverse of f of x is what? Here's your formula for f inverse of x. We replace x here with f of x. So we replace this x with f of x. And then we take the formula for f of x and plug it in here. And we do simplification. Negative 4x minus 4 plus 4 is just negative 4x. That's over 4. Divide 4x by 4, we get x, and we verified this. You got to verify both to verify that you have an inverse function. Okay? Now, if you verified one, but not the other, I'd probably give you 7 points out of 10, but I want to see them both. And that's the difference between a low C and 100%. Okay? So let's get to 10 points. Okay, good. Now, we need to find 106, where that is. It's covered on the creation of 107. So I have to find it. I'm going to pause for a second. Okay, 106 on piecewise functions. I screwed this one up the first time I did it, so but here's the official version. I put the score. Never mind. I just did something kind of careless. Okay, so f1 of x is your toolkit exponential. F2 is your squared function. F3 is reciprocal function. I give you 3 intervals. I tell you to draw the piecewise function that's equal to the function of your choice on the first interval, and a different function of your choice on the second interval. And on the third interval, a function is different from the one on the second interval. So you could do all 3 functions. You could do, in order, you do the toolkit exponential, toolkit squared, toolkit reciprocal. You couldn't do the toolkit reciprocal in this one because the domain of the toolkit reciprocal graph in your 4x4 rectangle, which is what we're stretching things to right now, doesn't go up to 0. It doesn't, and nothing between 5 and 0, negative 5 and 0, negative 0.5 and 0, and nothing at all at 0. So you couldn't use the reciprocal here, but you could use it here, and you could use it here. Now, what I chose to do though is I just use these first 2 functions because they can both be graphed in one rectangle. One square, 4x4 rectangle. It's the cool toolkit functions. So the red dot is at the origin. Okay, in both of these, the red dot is at the midpoint of the lower edge. So that's your origin. So there's your x-axis, which is the y equals 0 line, and your y-axis, which is the x equals 0 line. Make sure you understand that. It comes up a lot. Okay. Then I simply constructed a squaring function. You see this white graph. And that's a squaring function. And of course, I've written over the white graph from here to here with orange, and from here to here with orange, and you see it. And here's your exponential graph. You see most of that one, but I've drawn over that with a blue curve between here and here. Why did I do that? Well, I did that because I chose to use the squaring function of these 2 intervals and the exponential function of this interval. Okay. So every interval had a function different than the one before it. We don't care if this one has the same function as this one, because this one is right before this one. This one is, and this function has to be different than this one. Well, we do that, and then between -2 and -1, including -2 but not -1, we draw orange line. So at x equals -1, here's your point. X equals -2, here's your point. This point is included because this part of the interval is closed. This point's not included, so I do an open circle here, because negative one isn't included in that part of the domain. Okay. Now your exponential function goes from x equals -1 to x equals 0. That would be this interval down here. And there it is. Okay. And it's open dots at both endpoints because the interval is open at both endpoints. Okay. Then we go to this interval, which is closed at this end and open at this end. And notice there's nothing between 0 and 0.5. The domain of the function does not include anything between 0 and 0.5. And I made a mistake when I wrote down the domain. I was careless and get hungry. So anyhow, we see the function on this interval, there it is. On this interval, there it is. And on this interval here, there it is. Now the details are in the longer video. And then I just kind of copy it over here. Okay. Now I meant to copy it with just white curves in the graph, but I don't include the part of the squaring function between here and here because it's not part of the piecewise function. The part of the piecewise function, this interval, on this interval. So there it is on this interval. And here it is. On this interval. I didn't shade that in. Okay. So it's like this now. Actually, here I've drawn it now without all the construction lines, just to show you what it looks like without a lot of water. And there it is. And it's equal to x squared for x between -2 and 1. Equal to 2 to the x for x between 1 and 0, but not including 1 in this interval, not including 1 in this interval. And that's equal to x squared again. Starting at -1/2, including that point, but only up to for x equals 2. Now I wrote down the domain and I wrote it down wrong and I wrote it as 1, 2. And on another version of the problem, it might be the interval from 1 to 2. But here it's interval 0.5 to this interval, and you can read the problem and see that's the case. Now, briefly, if you chose to use each of the three functions, on different variables, you could sketch the squaring function and the exponential function in a 4x4 rectangle with the red dot in the middle of the lower edge. There it is. Throw in your construction lines, everything else. Label things. And then you could follow any one of these functions in the interval from -2 to 1, a different one from -1 to 0, but as I said before, it could be the reciprocal function and so forth. Now, how do you get the reciprocal function? Because it's in a rectangle, it's 4x4 rectangle, but the red dot's in the middle. So you have to have a rectangle here. Superposed on the other one. Fortunately, all the construction lines for the reciprocal function match construction lines that you get the squaring function. Okay. So it makes it fairly simple. Then you got a bunch of stuff down here that isn't part of this rectangle, but that's okay. All right. So you would use a graph that looks like that and then shade it on different intervals in the way that makes sense to you, in the way you choose. Okay, you choose which function on which interval. I also write the function now in its standard form. I can't type it out in that form. I could use LaTeX and put it in that form, but I simply don't have time. So it's written the way it's written. But when you write it out for your solution, you want to write it in the standard. Or write a good description that is equivalent to the standard form, but I recommend this form. What's the domain of this function? Could you ask that? The domain is all the possible x values. Well, the domain is this interval, union with this interval, union with this interval. Because that's where we said it was. No, I wrote this interval wrong. I put 1, 2 here instead of 0.5. And a little brain freeze there. So on the longer video, you will see 1, 2 there, 0.52 is correct. What's the range? The range consists of all possible y values. Well, the lowest y value we get is this one right here, where y is 1/4. We don't have any points on the piecewise function to go lower than this. But every point between here, every y value between here and here is taken just by this part of the squaring function. Okay. Now I've labeled the endpoints, 1/2, 1/4, 0, 1, and so forth. You can verify that. Or look at the other video where I explained it. But your bit range is 1/4 to 107 and 108 are on rate of change. 109 and 110 are also on rate of change, but they're in an applied context, and you want to be sure you understand what to do in an applied context, which is basically put all your information on the graph. Okay, and then go from there. There are other ways to do it, and if you do it correctly, okay, but I want you to get used to putting your information on a graph. So that's the easiest thing for most people to see. Okay. 107, your rate of change. You got f of -2 equals 2, and you also said that a point on the graph of f of x is 0, 1. You want to find the average rate of change of f of x on the corresponding interval. Now that could be pretty mysterious. I'm going to make it less mysterious for you. The key is represent all this stuff on a graph. So let's put this information on a graph. First of all, you set a coordinate axis. You got the point 0, 1. So, you know, we draw the line for y equals 1. We label it over here so we don't clutter up the axis. But right there's the point 0, 1. Okay. We also know that f to -2 equals 2. What does that say? Well, when x is -2, that means your y value is 2. So for x equals -2, which is represented by this vertical line, you got the horizontal line y equals 2, where they intersect is the point -2, 2, which corresponds to f of -2 equals 2. Point -2, f of -2 is -2, 2. That's the point. It's point 0, 1. I didn't label, but it's pretty obvious. So now we want to find the average rate of change. Well, we find change in the y and divide by the change in the x. That's easy to see on the graph. I say always draw that triangle. Okay. And this is a triangle you should be familiar with. Go from this point to this point, from left to right, we follow a path down and then over. Now we could easily have gone over and down. We draw the triangle up on this side of the hypotenuse, but I drew it down here, so I thought I might have more room to label things. I think it's pretty much the point. Anyhow, we get the rise. The rise is from here down to here. Well, from 2 to 1, your rise is -1. Go from 2 to 1, you go lower. Rise is -1. Of course, you want to write out the details. 1 minus 2, which means we subtract where we're going from where we are. Okay, we're going to 1, we're starting at 2, so it's 1 minus 2, and that does give us a -1. That's your delta y in any case. Your delta x corresponds to the run of this triangle, and the run goes from x equals, boy, I did a bonehead thing there too. Okay, so I made a mistake here. I gotta correct that now. Oh, too many more. Okay. We'll get that in a second. Okay. So our delta y over delta x, I said, was -1 over 1. Our delta y is -1, but our delta x is 2. So our Negative 1/2 is just negative 1/2. And that's the average slope. Now, we can associate that with the slope of this triangle. Box around it, put it above this hypotenuse of the triangle, the slope line. That indicates the slope is negative 1/2. Okay, so I was a bonehead error. Well, I thought that was one. I probably saw that one there. That's all I saw. Okay, I don't know. I do apologize for that error. 108 rate of change. You're given coordinates of 3 points. So you got the point for 1, 1. So you draw a line for x equals 1, line for y equals 1, and label. I really do want to see you do that. I won't necessarily penalize it if I don't see it, unless it's like with one of the constructions we have to label with construction lines. But I think it's a good idea no matter what. Gives you a better picture. Okay, so anyhow, x is 1, y is 1, that's the point 1, 1. Next point was probably 4, 5, yeah. So x equals 4, y equals 5, there's this point. The other point was given as 8, 8. Well, here's the point. 8, 8. So you draw a line for x equals 8, you draw a dotted line for y equals 8, and there's that. Now you find the rates of change. Then you represent that on a graph. Okay. So go from this point to this point, you're going to get the rise and the run, or the change in y and the change in x, and you divide, you're going to get the slope. And turns out I'm not going to go through all the details. Your rise here goes from 1 to 5, it's clearly 4. The calculation's 5 minus 1 equals 4, just to check to make sure you weren't cross-eyed when you did that, like I was when I did this thing up here. And then you go from here to here, and your run is 3. So your rise is 4, your run is 3. Your delta y over delta x. Average rate of change is change in y over change in x. Turns out, and that's 4 over 3. Turns out that's also the slope. So we can label it as a slope. We do the same thing here, and we label a slope. And then we do the average rate of change between x equals 1 and x equals 8, which is between the x is 1 point here and the x equals 8 point here. So now we have this triangle, this green triangle, gives us a big old average rate of change over everything. Okay, well, we calculate that, we get 7 for the delta x and 7 for the delta y. I think I did that one right. 1, 1 to 8, 8, not on 7 each way. Okay, and your slope, then your average slope is 1. And I don't know that I even labeled that. I should also put 1. Now, the question I ask on this is the average of your first 2 rates of change equal to the overall average rate of change? Okay. The overall average rate of change is 1. The 2 rates are 4/3 and 3/4. Rate from here to here, the rate from here to here. If you average 4/3 and 3/4, that means you add the 2 and divide by 2. Well, that comes out 25 over 24, which is close to 1, but it's not 1. It's like 1.04 something. Okay. It's not equal to the third average, to the overall average rate of change, let's say. The third average rate of change, the average rate of change that you calculate last between the first and the last point. All that the overall rate. Okay. So they're not equal. Now it's just an example of things that seems like they ought to be equal because you got 2 of them here, and now you got 1 between the first point and the last point of this path, and it doesn't work out. Now I will say that maybe it works out if these 2 intervals from here to here, the x intervals, if this x interval was equal to this x interval, maybe it would work out. Okay. You might even test that to kind of put this into a little perspective, although I imagine you probably won't have time. It'd be interesting to test it. Okay, well, that's these two problems, you gotta get one of these two. From like one of these two different numbers. On this one, the trick is you gotta understand that f -2 is 2 gives you a point on the graph so you can calculate the average rate of change. So I've kind of mixed up the way I've given you the information for this point and the information for this point. And that's the hurdle that you got to overcome. The hurdle here is understanding what I mean by the average of the two rates of change. It also expects you to be able to do calculations of fractions. Okay. Now we can move over to here, a couple more rates of change. Yeah, I'm gonna go on. This video's getting a little longer than I want it to be, but it's pretty easy to find things. On second thought, I'm gonna stop it here and start another.